Well, thank you very much for the invitation. So I would like to present basic steps and ideas of Voevodsky proof of Bloch-Kato and Milnor's conjecture. So let me first state the conjecture. Take a field F and a positive integer relatively prime to the characteristic of F. Now we have multiplicative group of separable closure of F, an endomorphism of raising to the nth power, which is surjective. And the kernel of this map is the group of roots of unity of degree m, mu m. This is m. And then we apply Galois homology groups. So H0 Galois invariance F star, raising to the m's power, F star again. Then H1 F mu n m, and then H1 F sep star. Well, the last group is 0, and it's the statement of classical Hilbert-90 theorem. Therefore, we see that the map from F star to H1, which we write as A goes to the class of A, is surjective. So this group is F star modular m's powers. Well, now we can extend this construction to higher degrees. We take a tensor product of some number of copies of F star, namely n times, n some non-negative integer. And we map it to Hn, F, and then mu n, and tensor product with itself, mu m, tensor product with itself n times. And the map takes a tensor A1, A2, An to the cup product of A1, A2, An. Then we observe that some elements always go to 0, namely elements of the form tensor A1, An, provided the sum of two entries, different entries, AI and AJ, is 1. So those elements go to 0, so you can factor out the tensor power by those elements. We get those relations called Steinberg relations. And the factor group is known as Milnor group Kn of F. Well, certainly the map factors through the elements divisible by m. So overall we get Kn m of F modular m. So Hn F mu m tensor power of m, and this is called the norm-residue homomorphism. And the Bloch-Kato conjecture states that this is an isomorphism. So this is the Bloch-Kato conjecture, and it depends on the two integers, on n, the degree, and m also. In the case when m is 2, this is the Milnor conjecture. So Milnor's conjecture is a special case of Bloch-Kato conjecture. So Bloch-Kato n2 is the Milnor conjecture of m. Well, there are easy reductions. First of all, we can easily reduce to the case when the integer m is a prime integer, m, and we call it L prime. Then we may assume that roots of unity of degree L are in the field. Xi L, primitive root in the field. Also, the case n equals 0 is exactly this one. So the statement of degree 1 is a direct consequence of Hilbert 90. So we can assume that n is at least 2. Okay. One of the basic ideas is to try to compare the normalistic homomorphism for different fields, and for field f and for some field extensions that appear usually as a function field of some varieties. And interesting varieties are so-called splitting varieties of a symbol. By the way, I should have said that the generator of K Milnor group is denoted by A1, AN, just the coset of the tensor product of A1, AN. So the Milnor group is generated by such symbols, and they are subject to obvious relations. It is multiplicative in each term and has Steinberg relation. By the way, the Bloch-Kato conjecture has a strong consequence, namely the homology group then are generated by the first component, as does K Milnor ring. And the only relations between the defining relations between the generators are given by Steinberg relations. So certainly Bloch-Kato conjecture is a very strong statement, imposes restrictions on the homology of absolute Galois group. So we call such an element a symbol, generator of Milnor group. And the first idea is to use so-called generic splitting varieties of symbols. Well, you fix a symbol, A1, AN. We view this in Kn Milnor modulo M, not modulo L now. L is prime. And we say that variety X over F, well, smooth projective, is called generic splitting variety. Of alpha, if the following two things hold. First of all, alpha, when you extend the field to the function field of X, it becomes 0. It splits over the function field of X. Second, if L over F is an extension such that alpha is split by L, then variety X has a point over L. So X detects existence, well, the splitting property of the symbol. Well, sometimes we do L generic splitting variety, which means slightly weaker condition that X has a closed point of degree prime to L. Okay, so the splitting varieties exist clearly in the following situations, examples. N is 2, the smallest interesting value. Then the symbol is just A1, A2. And we have the associated cyclic algebra of degree L for A1, A2 if you fix a root of unity. And then if you take the X, it's a very Brouwer variety. For this cyclic algebra, A1, A2, with some root of unity fixed, then the splitting variety. Very Brouwer variety has a point if and only if algebra is split. And dimension of that variety is L minus 1. Well, the second case, when you have Sorry?
X has a close point of degree prime to L.
the cyclic algebra of degree L here.
Yeah, but I mean, in this number 2, before.
The last few symbols of that number 2.
You asked it.
Prime to L.
Prime to L, yeah. Small L. Okay.
Okay, I want to because this example doesn't
X over L, yeah. That's what you mean.
over L.
X over L, yeah. Sorry. Now, the other extreme case, and L is 2. So we do cohomology modulo 2, and now alpha is the symbol A1, A2, AN. We can consider the following quadratic form, Q. It is the sum of two forms. One is a Pfister form, A1, A2, AN minus 1, which is, by definition, a tensor product of binary forms like that. Plus negative AN. So this quadratic form is isotropic if and only if the symbol is trivial. It shows that if you take for X a quadric, for the quadratic form, projective quadric of Q, it becomes a generic splitting variety for the symbol, modulo 2, and dimension of the quadric is L to the power n minus 1 minus 1. L now is 2, so 2 to the n minus 1 minus 1. Well, of course, you can present the symbol in such a way from very many tuples of elements. And clearly, the corresponding quadratic forms are not equivalent in the sense that they give the same quadrics. So the quadrics are different for different presentations. So there is no canonical choice of such a splitting variety. Although you can prove that all these quadrics are stably birational to each other, but it's not clear whether they're birational. Maybe not. So it looks like there is no canonical choice of X, but Rost noticed that nevertheless you can get a smaller piece than X. It's motif, which is direct sum or inside the motif of X. It's called the Rost motif, R alpha, direct summand of the motif of X of a quadric. It is a binary motif, which means that in the split case, R alpha is the sum of Z and Z d to d, where d is a dimension. This is dimension d. The motif of X in the split case has many terms, the sum of such twists of Z, but the binary motif, in general, it is not recomposable, and it's independent on the choice of presentation. So the binary motif is well defined by the symbol. So this is probably just the first indication that the motivic approach, motivic point of view, makes sense, at least, for this problem. So it's better to study the Rost motif, binary motif, rather than a motif of different quadrics associated with the symbol. Well, Rost and Voevodsky proved that for any n and l, generic splitting varieties exist. L generic splitting varieties exist, and moreover, you can get those which have dimension L to the n minus 1 minus 1. But we will need more properties of generic splitting varieties later, at least two important properties. And now, clearly, if you really want to do generic splitting varieties, then you need to understand what happens with those groups when you extend the field to the function field of a variety. For homology, you have some satisfactory technique of computing Hn of the function field. At least you can compute, you can define the Hn et al. For any variety X. For the left-hand side, things are much worse. You don't know how to define the Milnor group of a variety, but even if you write something, there is no machinery how to manage those groups. And in the original work, the Quillen K-theory was used instead of Milnor groups. But Quillen coincides with Kn Milnor only up to degree 2. So this approach was hopeless in general. So the second idea used by Voevodsky was, instead of doing Quillen's K-theory, do motivic homology. So there are two types of motivic homology. The ordinary one, they just depend on two parameters. X is a variety, Z twisted by Q, N and Q are those parameters. We will abbreviate this H N Q of X. Sometimes we will replace Z by any abelian group, very often by the localization of Z with respect to the prime ideal L. Well, but it will be clear which group is used each time. And the other group is the et al. Version of motivic homology, et al. Motivic. And we have a comparison map between those groups. Well, if you look at the ordinary group of motivic homology, it is often 0. So let me draw diagram. That is N, that is a twist Q. Then we have a line, N is twice Q. Is twice D. D is the dimension of the variety. And then there is another line, N equals Q. So for everything below, the motivic groups are 0. And non-trivial things are here. I'm talking about this group. And in general, it's very hard to calculate the value of motivic homology. But as usual, on the border, you can say something. For example, for those points on the first line, you have motivic homology to I. They, if X is smooth, the same as Chow groups of codimension I cycles on X. For the points on the other line, we have the following description: H2D plus S, comma D plus S, this is the point of the other line, is the co-kernel of the following homomorphism. The target group is a direct sum over all points of codimension D on X, in other words, all closed points on X. And here stays Ks of the residue field of the point, Milnor. And the first is direct sum over all points of codimension 1 less, D minus 1 over all curves on X. And here's Ks plus 1 Milnor of f of X. And this is so-called residue map. It turns out that those groups, especially when S is 1, plays an essential role in the Voevodsky proof of Bloch-Kato conjecture. So we know, at least this way, description of certain motivic homology on the border of this area. Also, when X is a point, from this description you get H II or SS of F, spectrum of F, is the Milnor group K S of F. So the term in the statement of Bloch-Kato conjecture appears to be a motivic homology. And this group is also but etal-motivic homology with coefficients in Z mod mz twisted by n. So the Bloch-Kato conjecture is nothing but a comparison theorem between ordinary and motivic and etal-motivic homology. Actually, one can state more conjectures known as Beilenson-Lichtenbaum conjecture. BL NL. It says the following, that for that this map between the two motivic homologies, H IN X with coefficients in Z localized by L. I mean, I invert everything but prime L to H IN et al. Is either for I between 0 and n plus 1, and monomorphism when I is n plus 2. So one can see that Bloch-Kato conjecture is a special case of Beilinson-Lichtenbaum conjecture. Moreover, there is another conjecture I would like to mention here. If you take X, the field, and the spectrum of the field, and I n plus 1, then by dimension consideration, the left-hand side is trivial. So the statement of BL is that H n plus 1 n et al. Of the field with coefficients in Z of L, Z localized by L, is 0. When n is 1, it is nothing but the classical Hilbert-90 theorem. So we call this generalized Hilbert-90. Hilbert-90 NL. So now we have three conjectures: Bloch-Kato, Beilinson-Lichtenbaum, and H90. They are very well related. As I said, the BL of NL implies the Bloch-Kato conjecture. Well, at least it implies H90, because H90 is a special case of Beilinson-Lichtenbaum. Then one can show that H90 implies Bloch-Kato, at least in the case when n is 1, that happened. Exactly, we used the classical Hilbert-90 to get the trivial case of Bloch-Kato. And then there is a nice paper of Voevodsky and Suslin showing that Bloch-Kato implies all general conjectures of Beilinson and Lichtenbaum. So all of them are equivalent. You choose one to prove. And the proof goes by induction by n, on n. And we always assume that all statements hold for degree n minus 1. It turns out that it is more convenient to work with the theorem of Hilbert-90. Sorry?
This conjecture, that is, we assume that X is varieties.
Yes, this is for varieties. This is for fields, and this is for fields only. So the statement for varieties can be reduced to the case of fields. Well, so now we try to prove Hilbert-90 for NL. Then you observe that H90 NL holds if the left-hand side group in Bloch-Kato is trivial. In other words, if every symbol is trivial modulo m. In this case, it's not hard to show that cohomology is trivial and Bloch-Kato holds, and in fact, it's not hard to show that H90 also holds. So now comes the idea. Let's split all the symbols. So take any symbol alpha A1, A2, AN, modulo M. And we take the splitting variety X alpha. And we look at the homology Hn plus 1 N, F. Again, the coefficients are in Z log L localized, Hn plus 1 N F of X alpha. Remember, we want to prove that this group is trivial. So the first group is trivial, but suppose we can show that it's an injection. And then we are done, because what does the first field do? It splits the symbol alpha, and then step by step you split all the symbols. And in the limit you get field with all symbol splits. So we get field with this property, for which we already know Hilbert 90. So in the limit, this group is trivial, but all such maps are injective. And we deduce that the first group is trivial. So the limit argument shows that sufficient to show this injectivity. For those Ital groups. Okay, here comes a third idea of Voevodsky, to use simplicial scheme. So the point is that varieties are so large that this group, even for variety, can be very, just some homology groups are very large. It's better to shrink X. And the way he does it, considers for any variety X the corresponding simplicial object, the two projections from X cross X to X, and three projections, and so on. So if X is a topological space, this stuff contracts to a point if X is non-empty. If X is empty, then it is empty object. If X is a variety, then it is a point, contracts to a point if variety has a point over the ground field. If not, it's some interesting object to look at. So over any extension over which X has a point, this gadget, the motif of which we will write curly X, becomes a point. It's a twisted form of a point. It's a motif of the simplicial scheme. And it turns out that, well, first of all, this very small object, because it's just twisted form of one point, and all interesting information is contained in homology of this gadget. Well, if you go back to that particular example of a Rost motif, which appears when L is 2, example L is 2, the Rost motif R alpha is decomposable if symbol alpha is not zero. But in the category DM, you can write an exact triangle using the corresponding motif of the simplicial scheme. There is a canonical homomorphism to X alpha, the motif of splitting variety. Well, the motif of that simplicial scheme of the of any, in fact, splitting variety of given of needed dimension. Then you can write here X alpha D twice D, and then D twice D plus 1. this is an exact triangle with some class, which is non-trivial in general. It is trivial if symbol is split. So we don't decompose R alpha as a sum of two motifs, but it's like an extension of a twisted form of a point by a twisted form of another simple gadget. Okay. Then Voevodsky restates the injectivity statement we need to prove. It is equivalent for a given alpha to the triviality of the group Hn plus 1, comma n, this curly x alpha. And it's the usual motivic, not a L motivic. Again, with coefficients ZL localized by L. So now it remains to show that certain homology group of the motif of the simplicial scheme of a splitting variety is trivial. Well, why is it simpler? Probably not that much, because we know almost nothing about homology of motivic homology of varieties or this curly axis. We know something. We know some motivic homology groups. And then comes another idea of Voevodsky to compare different motivic homology groups by means of standard operations. So the next idea is to use standard operations in motivic homology groups. So once I asked him how he got this idea to use standard operations, and he said, not by chance at all. He looked at the proof of Bloch-Kato in the case when n is 3, L is 2, and then noticed that the main point of the proof is to study a certain differential in the spectral sequence of Quillen for certain splitting varieties converging to high K theory. And this spectral sequence is analogous to the Atiyah-Hirzebruch spectral sequence in topology, where the first non-trivial differential is given by standard operation. So he noticed that there's nothing but standard operation that didn't exist in algebra at that time. So that's how he got the idea to define standard operations by analogy with topology. Of course, the difficulty is that the motivic groups are now numbered by two integers. So he defined operations called Milnor operations. On motivic groups, on motivic homology, Qi of by degree 2Li minus 1, Li minus 1. So it changes the degree by the first number and the twist by the other number. And as usual, the square of Qi is 0. The operation applied twice, you get 0. So you can define the homology groups. It's called Margolis homology. And just the kernel bunch of the image should be. And then, in certain situation, it turns out that Margolis homology are trivial. Well, the thing is that, as I said, the curly So X alpha is a twisted form of a point. But you can get even smaller than a point. There is a canonical morphism to the spectrum of F. And then you can take the cone of this guy. And so we split the point from X alpha. So this gadget is just this twisted form of 0. So really the smallest possible thing you can imagine, in general non-zero. And then the fact that Margolis homology for this particular object are trivial. So Margolis homology are trivial for I at most n minus 1. Alpha is that symbol of degree n. The reason why this holds turns out to be the following. Let's define the characteristic class Sn, which assigns to any vector bundle Sd a cycle of codimension d, 0 cycle on the variety. This is characterized by the property that if it have a sum of line bundles, so Li, classes of line bundles, it is just the sum of the powers of the first Chern class of those line bundles. So it's additive. And it belongs to Chow 0, Chow d of x, which is Chow lower 0 of x. And then we can compute the degree of such a cycle. If you take a variety and compute the degree of Sd applied to the tangent bundle Tx, you get an integer always divisible by L. Well, x here is of dimension, right dimension, L n minus 1 minus 1. But the point is that this number is not divisible by L square. And this property of splitting varieties they constructed was proven by Rost. And it's the first important property of splitting varieties. Probably they are called norm varieties with this property. And this property ensures that the Margolis homology for that object is trivial. Well, now we're almost done in the case when L is equal to 2. Let's do this case, L equals 2. In other words, we work on Milnor's conjecture now. So we want to show that Hn plus 1n of curly x alpha 0. But we apply a sequence of Milnor operations. The composition Q1 first, then Q2, and finally Qn minus 2. Well, each operation raises degree, and then you calculate. When a miracle happens, it is H2d plus 1, d plus 1, of x alpha. Well, almost the group we have considered, remember we did 2d plus s, d plus s, but it was a variety, now it's curly x. It turns out that this is almost the same. It is now homology of the Forlan complex. You take direct sum of over all points of codimension d minus 1 as before k n plus 1 a Milnor of residue field of points, the same for points of codimension D. So the same thing, but it was originally the co-kernel of this map. Now, because we have curly X, it's homology of the following complex, Kn of F, where the last map is the sum of norms. Here is the residue field of X, a finite extension of F. You just apply the sum of norm maps. And then Marcus Rost proved that this group is trivial. Oh, sorry. Just one, right. It's Ks, it's K1. And now it's K2. Yeah. So everything reduces to the case when S is 1. It looks like a miracle 2, but you can analyze the proof and see that the first, namely the first K1 plays the role, the multiplicatory group of the field. So trivial by Rost. It's probably the most complicated statement about norm varieties. And he uses a so-called chain lemma. So the triviality of that group is highly non-trivial. It's ingredient due to Marcus Rost. Now, let me draw a picture in some special case for the composition. So I would like to look at the case N is 4, L is 2. So the group we are interested in is 5, 4. Then we apply the operation Q1 to 8, 5. Q1. And then we apply Q2. It goes to 15, 8. Okay. Well, we have the other operation Q1 going from 3, 2, and the other operation Q1 going from 1, 2, Q2 now, sorry. And these 2 points are very close to each other. In fact, they are in a very small area of the formed triangle where by induction the homology are trivial. So those groups are trivial. So although those arrows are different lengths, being bigger and bigger, but the origin of all these things live very close to each other in the zero area, which means by triviality of the homology, Margolis homology, that each operation, Q1 here and Q2 here, are injective. So we got all these operations injective on corresponding groups by induction on the degree n. And we are done. The target group is 0, and then this group is 0. So the injectivity of single operations together with the triviality of the target group by Rost implies the result. That's how it works when L is 2. And that was the original proof of Milnor's conjecture. For Bloch-Kato conjecture, for L odd, this doesn't work because the target group is something which we don't know. It turns out that what is missing here is the Rost motive, which existed for L equals 2, the Rost motive, a binary motive. And Voevodsky was able to define the Rost motive using the symmetric operations, symmetric powers. So the fifth and the last idea is use of symmetric powers. you can define symmetric powers of objects in reasonable categories, provided you can divide by I factorial. And in our case, all integers less than L are invertible, so we can define symmetric powers up to L minus first. So what he does is the following. You take alpha and the corresponding norm variety and the simplicial object for the norm variety. In the following homology group, Hn plus 2, n plus 1, n minus 1, there is a canonical element, delta. It just corresponds to the symbol. It's trivial if and only if the symbol is trivial. Then you apply the same composition as in the previous case of the operations, and you get some other element mu, which lives in the group H 2b plus 1, comma b of x alpha. Now b is the following number, 1 plus L n minus 2. Well, this class gives you a homomorphism from H, gives you a morphism from X alpha to X alpha twisted by this B and 2B plus 1. It is given by mu. And then you can take exact triangles. R here is M alpha by definition, and that is X alpha of B to B. It defines binary motif M alpha, exactly the same as in the case L equals 2. It's binary because it has two components in the split case, binary motif. And the binary motif is the same as Rost motif when L is 2. But if L is not 2, it is different. And then Voevodsky used the symmetric power to define the Rost motif. R alpha, by definition, is the L minus first symmetric power of M alpha. And this is what is called the Rost motif. In the split case, the Rost motif is a direct sum of Z plus Z twisted by B twice B, and so on. Z of L minus 1 B, and then twice L minus 1 B. It has L terms. So it's not a binary motif, it's just L motif. And the main property of this motif is that it is a direct sum of the motif of splitting variety. So it is pure motif, in a sense. And it's a hard theorem. And it differs the case L odd and L equal 2. So R alpha is a direct summand of the motif of splitting of norm variety. Also, Rost defines what I call quadrangle. Maybe Rost also calls it quadrangle. Quadrangle. We concatenate two triangles. X, curly X alpha, X alpha L minus 1 B twice L minus 1 B, then the Rost motif B twice B, and then the Rost motif, and then X alpha. You can split it into two distinguished triangles. And what happens in the split case, you have the Rost motif like this. You add an extra term, or maybe here just LB. I don't remember. When you shift by B twice B, what happens, this thing shifts to the right. And you get extra term on the right, and then you have to delete Z. That exactly is encoded in that distinguished quadrangle. And using exact sequences corresponding to this quadrangle, you do the following. And it's the last step in the proof. You want to show that H n plus 1 n X alpha is trivial. You apply the sequence of operations. But now Q1, Q2, up to Qn minus 1, one more operation. So we arrive in the following group, H 2BL plus 2, BL plus 1 of X alpha. And using exact sequences corresponding to this quadrangle, we got a surjection from our friend H2D plus 1 D of curly X, which is 0 by Rost. So this surjection for this group is 0. And again, the composition of the operations exactly in this range up to n minus 1 are all injected because of triviality of Margolus cohomology, which implies that this class group is 0. And that completes the proof of Bloch-Kato conjecture in general. So you see that the proof is complicated technically, but it uses at least 5 ideas. All of them are very non-trivial, very original, and overall, the statement of Bloch-Kato conjecture represents a masterpiece in algebra, one of the best statements in algebra I know. Okay, thank you.